Section 1. Introduction. The Bimolecular Elimination Paradigm. Last time, we focused on substitution, specifically, how nucleophiles take the place of leaving groups. But to design a truly effective synthesis, you must master the pathway that's always in competition with it. In this lesson, we're going to dive deep and master the E2 mechanism, also known as bimolecular elimination. While substitution replaces one functional group with another, elimination constructs a new structural motif, the pi bond, by the simultaneous removal of two substituents from adjacent carbon atoms. The numeral 2 in E2 is the kinetic signature of the reaction. It signifies a bimolecular rate-determining step, meaning the reaction's success depends on a properly oriented, high-energy encounter between the base and the substrate. When we derive the rate law in the laboratory, we observe that the reaction velocity is directly proportional to the concentration of both participants. In this second-order kinetic regime, the concentration and effective basicity of the base are not merely influential. They are decisive. Unlike SN1 or E1 reactions, which wait for a slow ionization step, the E2 pathway is direct and concerted. A strong, reactive base dictates the pace of chemical change, forcing the molecule to reorganize its bonding architecture in real time. Section 2. The concerted mechanism, the synchronized flow of electrons. The hallmark of the E2 mechanism is that it is concerted. In the language of physical organic chemistry, this means the reaction coordinate consists of a single continuous slope leading to one transition state. There are no carbocation intermediates and no discrete, isolable carbon ions. The electronic dance begins when a strong base approaches a beta hydrogen, specifically, a hydrogen attached to the carbon adjacent to the one bearing the leaving group. As the base begins to abstract this proton, the pair of electrons from the CH bond does not simply disappear. Instead, it shifts toward the region between the alpha and beta carbons, initiating formation of the carbon-carbon pi bond. Simultaneously, the bond between carbon and the leaving group polarizes and cleaves. At the transition state, this energetic summit, multiple electronic events occur simultaneously in a single concerted step. The base hydrogen bond is forming. The beta-CH bond is breaking. The CC-pi bond is developing. The carbon-leaving group bond is breaking. Although partial carbon ionic character develops on the beta carbon in this transition state, no true intermediate is formed. All bond-making and bond-breaking events are inseparably coupled. This synchronized flow of electron density is why E2 is often described as a push-pull mechanism. The base pulls the proton, while the resulting electron density pushes the leaving group out. Because these events are coupled, the transition state adopts a highly specific geometry that maximizes orbital overlap and minimizes electronic repulsion. Section 3. Stereochemistry, the anti-periplanar requirement and orbital synergy. E2 reactions are not only fast, they are remarkably strict about molecular geometry. For elimination to occur, the beta hydrogen and the leaving group must adopt a precise spatial arrangement known as anti-periplanar. In this conformation, the hydrogen and leaving group are positioned 180 degrees apart in a staggered arrangement. While this geometry minimizes steric strain, the fundamental requirement is efficient orbital alignment during pi bond formation. From the perspective of frontier molecular orbital theory, the reaction involves a concerted flow of electrons. Electrons from the breaking CH sigma bond contribute to the developing pi bond, while electron density simultaneously accumulates in the Cl sigma star antibonding orbital, leading to leaving group departure. This donor-acceptor interaction requires precise phase alignment, which is only achieved in the anti-periplanar geometry. Here, the internal lobes of the relevant orbitals face each other directly, creating a continuous pathway for electron density to flow across the two carbons. As electron flow begins, the base abstracts the proton, and the carbons develop partial trigonal planar character. Notice on the screen how the carbons progressively acquire p orbital character in the transition state. For a successful reaction, these emerging orbitals must achieve proper orbital alignment. Only when they are properly parallel can they overlap side by side to form the new pi bond. This orbital synergy requires the CH and Cl bonds to be in the same plane, but in opposite directions, the anti-periplanar arrangement. In contrast, the syn-periplanar geometry results in poor orbital overlap and severe torsional strain. Consequently, E2 elimination proceeds exclusively from the more stable staggered conformation, where the activation barrier is lowest. This strict requirement leads to remarkable stereospecificity. In rigid systems like cyclohexane rings, where free rotation about CC bonds is prevented by the ring framework, E2 elimination occurs only when both the beta hydrogen and leaving group are axial, creating a trans-diaxial relationship. If the leaving group is equatorial, the necessary coplanarity of the reacting bonds cannot be achieved without a conformational change. Only after a chair flip brings both groups into axial positions does elimination occur. Owing to this geometric constraint, chemists can predict, with high precision, which alkene stereoisomer will form. Section 4. Regioselectivity. Navigating the Zaitsev and Hofmann crossroads. When a substrate contains multiple types of beta hydrogens, the base faces a choice. This introduces the concept of regioselectivity, the preference for bond formation at one position over another. Under typical E2 conditions, eliminations follow Zaitsev's rule. The most substituted alkene is formed as the major product. The rationale is thermodynamic. Alkyl groups stabilize alkenes through hyperconjugation, and because the E2 transition state is often alkene-like, formation of the most stable alkene corresponds to the lowest energy transition state. However, this preference can be deliberately overridden by employing a bulky, sterically hindered base, such as potassium tertiary betoxide, or LDA. The base can no longer easily access crowded beta hydrogens. Instead, it abstracts the most accessible, least hindered proton. The result is the less substituted alkene, known as the Hofmann product. By adjusting the steric profile of the base, chemists gain direct and reliable control over the regiochemical outcome of the elimination. Section 5. Substrate effects. Why elimination thrives on substitution. A striking contrast exists between substitution and elimination. While SN2 reactions are severely hindered by steric bulk, E2 reactions often benefit from it. Methyl substrates, for instance, are completely incapable of undergoing E2 elimination, as they lack the necessary beta hydrogens required for the reaction. Primary substrates are small and accessible, making them ideal candidates for SN2 reactions. E2 is typically a minor pathway, unless a bulky base is employed to suppress nucleophilic substitution. Secondary substrates occupy a mechanistic crossroads, where SN2 and E2 pathways may compete depending on base strength, steric demand, solvent, and temperature. Tertiary substrates, however, are ideally suited for E2 under strongly basic conditions. The backside attack required for SN2 is sterically blocked, while elimination leads to a highly substituted and therefore more stable alkene. As a result, E2 proceeds rapidly and efficiently. Section 6. The base and solvent, optimizing the reaction environment. The E2 mechanism is fundamentally base-driven, unlike SN2 reactions, which rely primarily on nucleophilicity for carbon attack. E2 reactions depend more heavily on basicity. In this pathway, the decisive event occurs in the concerted transition state, where a beta proton is abstracted rather than a carbon being attacked. Commonly used bases include hydroxide and alkoxides, such as ethoxide or methoxide. Bulky bases, such as tertiary butoxide, are particularly effective as they preferentially promote elimination over substitution. This is because steric hindrance disfavors the crowded approach to a carbon atom much more than it hinders the abstraction of an accessible external proton. For particularly demanding eliminations where a higher activation barrier must be overcome, very strong bases such as sodium amide may be required. Solvent choice also plays a critical role in tuning reactivity. Polar aprotic solvents, such as DMSO or DMF, weakly solvate anionic bases. This increases the effective basicity of the reagent, facilitating proton abstraction in E2, while also increasing nucleophilicity and accelerating SN2 reactions. In practice, however, chemists often employ the conjugate alcohol of the base as the solvent. For example, using sodium ethoxide dissolved in ethanol. Although this creates a protic environment that reduces nucleophilicity more significantly than basicity, substitution becomes strongly disfavored, especially for tertiary substrates. When combined with high base concentration and elevated temperature, elimination is favored over substitution, leading to a selective and efficient E2 outcome. Section 7. The leaving group, the art of departure. The efficiency of an E2 reaction depends on how effectively the leaving group accommodates the developing charge, as the carbon-leaving group bond breaks in the transition state. Simply put, the best leaving groups are weak bases, the stable conjugate bases of strong acids. A better leaving group lowers the energy required to cleave the carbon-leaving group bond in the concerted transition state. This is why larger, more polarizable ions like iodide leave more readily than bromide or chloride. For even greater reactivity, chemists use sulfonate esters like tosylates. Their exceptional ability comes from resonance stabilization, which spreads the negative charge across 3 oxygen atoms. By facilitating bond cleavage in the transition state, a high-quality leaving group lowers the activation barrier and accelerates the elimination rate. In summary, the E2 mechanism is a concerted, bimolecular elimination that forms alkenes in a single, highly coordinated step. To design a successful synthesis, you must optimize the following 4 factors. First, the substrate. Select secondary or tertiary substrates to favor elimination over substitution by disfavoring SN2 pathways. Second, the base. Use a strong base to increase the rate of proton abstraction. Bulky bases strongly favor elimination by disfavoring carbon attack. Third, the solvent. Polar aprotic solvents increase base reactivity, while using the conjugate alcohol with elevated temperature slows substitution and biases the reaction toward E2. Fourth, the leaving group. Choose a superior leaving group, a weak base that stabilizes electron density in the transition state, lowering the activation barrier and increasing the elimination rate. However, even when these 4 factors are aligned, the E2 reaction demands one final prerequisite: the anti-periplanar stereoelectronic requirement. The beta hydrogen and leaving group must adopt the proper geometric alignment for elimination to occur. By strategically choosing base size and analyzing substrate geometry, chemists can bias the reaction pathway toward elimination and effectively suppress competing substitution. E2 is not merely a competing side reaction. It is one of the most reliable methods for constructing carbon-carbon double bonds, a fundamental framework throughout organic chemistry. To wrap up, take a moment to examine this final comparison table, which illustrates the decisive competition between SN2 and E2. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.